Thank you. Okay. Hello, everyone. Welcome to this week's Colloquium. Just a few notes before we get started. So, first of all, feel free to grab some tea. And today, we have a good presentation from L1, who is presenting about climate change and nuclear fusion. So, let's give a big round of applause.
Thank you. So, welcome to my colloquium. I'm going to get started immediately. Basically, the current state of affairs that we have right now in the world is that basically the entire goal of what they set in place at the Paris Accords a while back, which we haven't definitely not followed, was to limit global warming to 1.5 degrees or at most 2 degrees. Basically, the idea was we didn't want to go to 2 degrees. As you can see, what we've implemented right now is the red line, and there's a pretty wild uncertainty on where it's going to go, but it's way above how far we're going to go. And it's leading to a warming of on average 3.2 degrees Celsius, which is way worse than we wanted, and definitely not like the goal that was set out. So we're going to see later why this is important, why it's a problem. So what we really need to see here is that to reach these lower emissions and these lower temperatures, we need to get emissions to go down right now as fast as possible. Right, we need a very sharp drop immediately. And here we have that basically this is what happens if we don't drop, right? If we get that 3.2 degree increase in temperature, we're going to have about in the middle here. So we get, for example, heat and humidity, right? We all know, not very fun. At some point, it gets very dangerous for the human body. And at this point, this is where basically every day of the year, you live in a space that is extremely dangerous for your life. So a lot of South America, a good chunk of Africa, and a lot of Oceania basically become unlivable. So, and that's projected to happen in not a long time, by 2100. So 2100. So this is really this isn't a long-term problem. This is going to happen basically in our lifetimes if we don't do anything. More impact, so food production. So we get, again, around the middle section, basically an enormous amount of the world wouldn't be able to produce as much food as possible, especially, once again, Oceania, China, India, and a good chunk of the Americas as well. So this is going to impact food production, which, with population still increasing in the world, is going to be a massive problem. And an enormous loss in the amount of fish we get as well, which a lot of communities, especially around Oceania, again, need to survive. An enormous amount of people in the world actually rely mostly on fishing industries. So this is definitely a massive issue that's going to happen. If you have any questions on where this data is coming from, it's coming directly from the IPCC reports on climate change, which come out. They have some reports every year and then some every 5 years. It's all available online. So the future, we've seen the consequences that this can bring. What we need to do is rapidly and strongly reduce greenhouse gases emissions. We know that we have right now a lack of appropriate government response. I wrote this before Trump was in office. Now it's going to be even worse. We're going to have, and so now the question is, how can we lower these emissions, right? We know that the policies we have in place right now are not enough. So we have existing technologies. We have lots of ways to reduce emissions that already exist. And we also have to look at new technologies. So this is where the main topic of this talk is really going to come in, which is nuclear fusion. So nuclear fusion, as in this talk, is going to be mostly focused on as a non-GHG emitting energy source. So it's used to produce most electricity. Ideally, it would be an energy source that produces no long-term nuclear waste and has widely available fuel throughout the world. This is the ideal conditions. We'll see later why that second part isn't necessarily always true. But that's the goal of this idea that people have been talking about for a very long time, and that now is becoming more and more research, with the intensity of the problem that we've seen before really pushing a lot of people to invest heavily in this research. So the basics. Fusion happens naturally in stars. So basically, for fusion to happen, you need this matter to be in the fourth state of matter, which is plasma. Basically, I like this diagram. It shows pretty well what happens. Basically, the nuclei and the electrons split when they're under a very intense heat and pressure. So you get this charged goo of sorts. This is necessary because if you want fusion, basically the idea of fusion is you have two nuclei that will fuse together, that collide, right? You can't have that if you have the electrons outside repelling each other. So the stars have multiple pathways to fusion. It's a really complex topic, and that's basically how all the elements we have here on Earth and everywhere else in the universe are produced. We won't be discussing that here because it's complex and an entirely different branch of physics, basically. Uh, and then what is necessary to fuse nuclei? So to fuse nuclei, you need to get them to accelerate fast enough, or have enough kinetic energy that it will overpower the repulsion of the electromagnetic forces pushing them away, right? Because you have two nuclei, they're both positively charged. If you try to force them together, they're going to repel. You need to have enough energy that they collide and they stick together, basically. So stars can do it because they're extremely hot and extremely dense. So they're extremely tightly packed, and the particles are already moving very, very fast. And it produces energy by E equals mc squared. We'll see a bit later how exactly that happens. So basically, they lose a bit of mass and return a lot of energy. So here's the idea of the graph, which is going to explain why fission and fusion both work, which can be a bit confusing. So when we have fission, which is taking a really big nuclei and splitting it up into two smaller nuclei, we're taking these extremely heavy nuclei here, like uranium-235 or 238, these kind of things, and we're splitting them into nuclei that are higher up the chain. When we're doing fusion, we're taking these extremely small nuclei and then fusing them up the chain. Basically, the idea of this is everything wants to eventually get to iron. Iron is like the stable element, and the more you split or fuse to get closer to iron, you're always going to be releasing energy. So this works because between elements in the nucleus, there's this binding energy, and if you're really, really big, the binding energy gets a bit smaller, and when you go back up, you'll get that iron is the one with basically the most binding energy, and then if you go this way, you also have lower binding energy when you're here. So basically, it's always, if you want to produce energy through fission or fusion reactions, it's something that's really big and go towards iron, or really small and go towards iron. So we see that fission here releases much less energy than fusion. Fusion is going to release a lot more energy because we're starting a lot lower and going a lot higher. Right? This is the average binding energy per nucleon in these nuclei. So if you're going to take a very, very small thing and fuse it up to, let's say, here, this difference is much greater than the difference from uranium to whatever it makes, right? Like, it's just pretty well visualized. You get a lot more energy from fusion than fission. That's why it's seen as this kind of perfect energy source. Did I skip a slide? I did not skip a slide. So basically, the goal is to make a star on Earth, right? Basically, make the process that happens in stars, but make it happen on Earth. So why do we want to make a fusion reactor? As we said before, the goal is to have basically near infinite energy, and for it to be safe, and for it to emit no or very few greenhouse gases. So it's safe because there's no chance of a nuclear fusion reactor having a meltdown, basically, or at least not a dangerous one. Because what's going to happen is, to have nuclear fusion, you're going to need the plasma inside the reactor to be extremely hot, right? If the plasma ever expands outside of the reactor, let's say the reactor breaks down, plasma leaves, it's going to cool down incredibly fast, and therefore the reaction is going to stop immediately. So there is no risk of basically your reactor turning into a bomb. That just cannot happen. The idea of near infinite energy is that we'll talk about it later mostly. Basically, the idea is that you can do nuclear fusion with elements that are pretty readily available on Earth. The difficulties, however, and there's a lot of them, and they're complex because we still haven't achieved this, and we've been trying for a very long time. Firstly, achieving kinetic energy needed for the reaction is incredibly difficult. You need enough energy to collide them, right? As we talked about, stars can do it because they're incredibly massive. Now we need to get the amount of energy in a star, basically, into something that can fit on Earth somewhere. And then we need to control the reaction, right? We need to contain this extreme amount of heat in condensed matter and control it into a space, and then somehow transform that heat into energy. And then we just sustain the reaction. So we need to control it, and we need to keep it going for extended periods of time so that we can create long-term energy and not just short bursts, right? And the idea is then to make Q greater than 1. So Q is a ratio of energy into energy out. So the idea is you want to put in, let's say, X amount of energy, you want to get in more than X, right? You want to get more energy out than energy in. So the idea here, you don't need to look at all the details on this chart. It's just a representation of the different types of fuels you can have for fusion. These are all like nuclei, and the amount of energy they release and what kind of radiation they emit. So if we look at just, for example, purely what releases the most energy, deuterium, which is D, which is hydrogen with one more neutron, plus 3 helium, which is helium with one less neutron than usual, releases the most energy. Actually, no, deuterium plus lithium releases the most energy. Never mind. But the problem we're going to have with the amount of energy that's released here is the bigger the nuclei, the harder it is to fuse them because you have a stronger charge, right? Pretty basic physics here. Stronger charge, more force between them, harder to fuse them. So in fact, in the end, what's been calculated as being the easiest fuel and the best fuel is this top line, which is DT fuel, deuterium tritium. So deuterium is hydrogen with one extra neutron. Tritium is hydrogen with 2 extra neutrons, so it's 2 neutrons, 1 proton, so tritium 3, deuterium 2. This basically has the highest energy. It gives you the highest energy for the smallest amount of energy you're going to put in. I'm simplifying a little here, but it's a combination of how much energy you're going to put in, how dense it's going to be, how hot it's going to be. And basically, it's quite clear that it's just the better alternative. So the problem with this is that tritium is actually not very tritium is extremely rare. So deuterium is abundant on Earth. We have an incredible amount of deuterium. Tritium is extremely rare. It's got a very short half-life of 13.7 or something like that years. So tritium is extremely rare. We have very little of it. And whenever we have some of it in 13 years, you have half of it. So if you don't use it instantly, you lose it. So one of the actual big problems with nuclear fusion is how to produce more tritium. We won't be covering a lot of that in this talk because there's not enough time. So you have 2 isotopes of hydrogen. You need to heat the plasma to at least 100 million degrees Celsius for typical reactors. And now the questions are, how can we reach that much temperature? How can we insert that much energy into the plasma? How can we control, as we said before, and how can we create this ignition? So ignition is when the reaction has gone on, the reaction has started, it's fusing, and it's producing enough energy that it's sustaining itself. So you have a self-sustaining reaction, it's producing energy. You can take a bit of energy out to make electricity or something, and then keep that reaction stable and keep it in there while it works on its own. That's ignition. So magnetic confinement. So we're going to cover 2 main types of reactors, magnetic confinement reactors and inertial reactors. So magnetic confinement reactors work by basically making a really strong magnetic field around the plasma, which is a charge, as we saw before, right? There's the electrons and neutrons. Electrons and nuclei, sorry, are separated, right? So this plasma is ionized, and we create a very strong magnetic field around it to trap it into a certain shape, depending on the reactor, different shapes. And we have the plasma spinning inside the reactor to keep it in movement, which makes it a lot more stable, and you can't really confine something if it's not in movement in the magnetic field. And also, one of the main advantages of this is this means that the plasma isn't touching the reactor, because you can imagine if you have something that's 100 million degrees Celsius touching anything known to man, that thing is burning down and melting instantly, right? So you need a method of containing it so that it doesn't touch the reactor. So how do you create this plasma? So basically, you're going to take a very hot gas of deuterium and tritium, you heat it up, and you send an electric current through this gas. And this is going to rip electrons off the atoms and create this ionized plasma. And through the resistance of the plasma, this will generate heat, right? Just resistance, electricity, heat. Yeah, there's also lots of other methods to heat plasma. Basically, one of them is to just shoot neutrons into it at very high speeds to just add energy, which doesn't perturb the charge because it's neutral. Now we're going to look at tokamaks. Tokamaks are like the main, most well-known type of nuclear fusion reactor that we have. So basically, they're big donuts, and they use extremely powerful electromagnets to create a magnetic field inside the chamber. So you have these big chambers that are kind of donut shape. We'll have a picture on the next one, the next slide. The world record for how long these can hold well, this was written a while ago, so it might have changed, but probably not. The world record for how long it can hold a plasma at the correct temperatures for fusion is only 1,056 seconds. So this is something that if we want to make nuclear fusion viable for an energy source, will need to be increased, because if you have an energy source that goes for 1,000 seconds and then shuts off probably for like an entire day of preparation, that's not something our modern grid can really support. That's going to be an intense peak in production of electricity and then a drop, and it's not really useful. So how do we actually make electricity from this? So basically, as we saw earlier, I'm going to go back a few slides. We see that deuterium and tritium, when fusing, make helium-4, which is the normal helium kind, and a neutron. And this shows how much energy each of these particles gets. So we can see the helium has much less energy than the neutron. So what's going to happen is this neutron, with an immense amount of energy, is going to shoot out of the plasma because it's not affected by the magnetic field, right? It's going to shoot out of the plasma and it's going to hit the reactor wall. When it hits the reactor wall, it's going to transfer that energy to the reactor wall. The reactor wall now gets heated up, and that wall is now going to heat water. Water turns into steam. Steam turns turbines, just like a normal power station. That part's quite simple. And turbine turns, makes electricity. So now this poses another problem. We now need to find a material. Now need to create a surface that can absorb these neutrons without taking too much damage, because neutron radiation is extremely damaging to all kinds of things, right? And all the infrastructure around the reactor has to be very resistant to neutrons as well. So, for example, let's say you have a valve to shut off and turn on how much water is going in to the behind the walls, right? That valve could get damaged by the neutron radiation over time, and it's imperative that it stays and works and functions, because if at some point suddenly you can't turn on the valve, you're gonna have like enormous amounts of problems, right? So you need everything around the reactor to be extremely like protected and make sure it's tested to make sure it's not damaged. And that's a problem with all the reactor kinds we're going to see later. So that's basically it. You heat the walls. Now we're going to look at the biggest tokamak in the world, which is still in construction in France right now, in Cadarache. So this is worked on by the EU and 6 countries. 6 other countries, so Russia, the US, Korea, Japan, and China. I feel like I'm missing India. I might have messed up. I don't think Japan's on it. Maybe Japan's not on it. So that's my bad. I should have memorized that. This basically ITER is an absolutely massive nuclear fusion reactor that they're building. It was meant to start its first fusion, like its first plasma, in 2025. It's way behind schedule, like most extremely big new enterprises are. It aims to produce a Q of 10, so again, the energy efficiency. So it aims to take in 500 megawatts of power and to output 50 megawatts of power in, and to output 500 megawatts of electrical power. So, well, however, ITER isn't actually going to be used to produce electricity, because the problem is it's basically a test concept. It's mostly for research. The amount of energy it would provide wouldn't actually be able to necessarily be very helpful to the grid, especially since the grid around it isn't developed in the way you would need to have these bursts of electricity, as we said before, be useful. So it's not going to actually convert that energy into electricity. It's just going to be made for research, and the water that's going to be used is going to be just evaporated into the air, because we don't have a proper setup of electricity around to use it, and it wouldn't create the amount of power it would create wouldn't necessarily be powerful enough that it would, basically the amount of money you would need to make the grid around and support this kind of energy wouldn't be worth the amount of power we're going to make from ITER. It's going to have electromagnets. So basically, this is the chamber, right? You have the central donut kind of, and the donut shape around it. The plasma flows inside of this, and through the center and on the outside, there are massive electromagnets. So these electromagnets are going to be cooled to 4.2 Kelvin to reduce electrical resistance, right? The entire idea is lower temperatures, a lot less electrical resistance. And while the plasma inside this confinement chamber will reach up to 150 million degrees Celsius. So now this is a whole nother problem. Now you got to think about, how do you make the hottest thing on Earth cohabit with basically the coldest thing on Earth in a range of like half a meter, if not maybe a meter. So now you've got to get extremely complex thermal shielding in between these two so that the water that takes in the heat doesn't touch the electromagnets, of course, but doesn't even get close to them because you don't want them to heat up. So some statistics, it's meant to have 840 cubic meters of plasma in this. So like this is an absolutely massive installation. As we said, it was meant to have its first plasma in 2025 and its first fusion in 2035. It's massively behind schedule because of a few problems. One of those problems is what they've done actually to make this fair to all the countries participating is each country builds certain parts of the reactor. So for example, the electromagnets in this middle section are constructed in the US, and then they're shipped over to France, and each country has to ship over these parts. And when they arrive, sometimes there's problems with when they try and put them all together, and so they have to be rechanged and have to change some parts. Also, there was problems with the start of the war in Ukraine, which made it hard to ship stuff from Russia. So because Russia's a part of this, it made it really hard to work with Russia and to get the shipments of materials that they need from Russia to build a reactor. So the first plasma will definitely not be in 2025, and it's definitely still going to be at least I'd say 2027, 2028 until we get the first plasma ITER. So now we're going to talk about a different kind of reactor, which are called stellarators. So stellarators are a much more complex reactor design. They're not this donut shape. They're kind of twirling shape. We'll have an image on the next slide because it couldn't fit here. They flow the plasma in a pattern that reduces energy loss using planar and non-planar magnets. I'm going to be honest, this goes into a field of physics I'm not good enough to understand and fully comprehend. All I know is that it spins the plasma, it compresses it more, it has a higher density, and using these higher densities, you don't need to go as high in the temperatures because, again, basically, it's a ratio of how much density to temperature you have. We need to go at temperatures of 100, 150 million degrees because we don't have as much density on Earth, right? Stars aren't that hot in their core, but they're so much more massive that they have the density such that they don't need the temperature as much, right? This reduces the amount of energy you need to start the reaction, which is really helpful because you don't want to have to put in extreme amounts of energy to start the reaction. And because you're making them you're making it denser, you get a better like energy profile. You get more energy out per energy in. They also operate for longer. So the Wendelstein 7X in Germany, which is being built right now, is set to hold plasma for 30 minutes, while I'm pretty sure ITER isn't going to hold plasma for much more than a minute. So you can see here that I believe, for example, stellarators, this is a personal belief, stellarators will be, if we get stable nuclear fusion meant for electricity production, stellarators will be the optimal way to go because they're, for now at least, they hold plasma for much longer periods of time, which is what we need if we want to have a long-term solution that actually produces electricity in a viable way. Because as I said, we can't have these spikes of electricity in the electrical grid. This gives it more time to fuse atoms and produce energy, so overall also just more energy overall because you have more time to fuse, right? So this is the design. We can see the tokamak, pretty simple in design-wise, basically a donut with all these electromagnets around it, while the stellarator has all these weirdly shaped, curved electromagnets with the plasma just kind of twisting around. So in these bends and things like that, it gets more compressed compared to the tokamak, where it's a lot more expanded. And they're a lot wider than tokamaks. Tokamaks are very circular. Stellarators have this much wider open space in the middle, and they've got this funky shape going on. So now we're going to look at a completely different type of fusion. This is inertial confinement fusion. So inertial confinement fusion reactors don't use electromagnets. They go inside on the idea that instead of confining plasma for a very, very long time, we can just use an incredible amount of energy in a very, very short time to produce a very short fusion reaction and then have that be the energy production. So they use the inertia of particles. So the idea basically, you just have particles smash each other really fast to achieve fusion through very intense compression. of a very small pellet of fuel. So comparatively to the tokamaks and accelerators, which use very big amounts of fuel, very massive, these use extremely small pellets of fuel that are going to be compressed extremely hard. So what happens is basically you have a small pellet of deuterium and tritium, and then it's encased in often diamond, a very small sheet of diamonds that is compressed uniformly, and then it's compressed often through the use of lasers, as we'll explore. So you have a Hochulrum, which I might have pronounced that wrong. I still don't know. It's basically an extremely small cylinder, about the size of a penny, so extremely minuscule, with two small holes on the top and the bottom. And basically, you shoot lasers into those holes. The lasers hit the sides of the Hochulrum, and the lasers, the Hochulrum, which is gold and a lot of other heavy material, transforms some energy of the lasers into X-rays, which will then kind of surround the pellet of fuel. The pellet of fuel gets surrounded by these X-rays, and it compresses the pellet of fuel. And you have to do this because it's basically the only way they found to uniformly compress the fuel pellet. If you try and shoot the lasers directly at it, you're going to get spots of energy, which are going to create immense disruptions in the fuel, and the fuel will go swirling around everywhere, which is not what you want. You want it to compress in one spot, and this is the way they found to do it. Then the fuel pellet compresses. All the nuclei of deuterium and tritium get incredibly compressed, very close together, and this energy is what causes them to fuse. And once a few of them fuse, they release energy to the others, and this starts a fusion reaction. So that's how they get their ignition moment. The plasma then, as soon as the fusion happens, you get the fusion. A lot of heat is released, so the entire plasma becomes a gas and expands, and it transfers all of its energy to its surroundings, so the air around it, and this causes it to cool down, and the reaction stops. And this lasts 10 billionths of a second, so it's an extremely fast reaction. The lasers shoot, transfer X-rays, and then it compresses, get the energy, it expands, and it stops. The problem with this is because it's so short, you don't get a lot of energy out of it, right? That's also why it's used small pellets, because using a bigger pellet wouldn't really be useful because you wouldn't fuse the entire pellet. You have to use a small amount because that's all you can fuse in that short period of time before it expands and uses it all up. So this method completely ignores the idea of confinement. Basically, it's really just you go for it, you give it a big shot, and then you let it expand. So this is actually the first method which has achieved ignition. So the idea of getting out more energy than you get in. So this is the first ever. They managed to do this December 8th, 2022. The Lawrence Livermore National Laboratory, which is a military laboratory in the US. So this was for military research reasons, but they made a big show of it being really important for the news, and they got more funding from the government for it, so sure. Basically, they shot 192 lasers at the Hochulrum, so this is a much better design than I could explain. Basically, you got to think of this as the size of a penny with a tiny fuel pellet encased in diamond. This is all gold and heavy elements. The lasers shoot through this tiny hole, hit the capsule, turn to X-rays, and hit the fuel capsule, compressing it, and that's where the fusion happens. So they've gotten an input. Basically, they calculated that the X-rays, only the X-rays, inputted 2.05 megajoules of energy into the pellet, and the fusion reaction that ensued, they managed to get 3.15 megajoules off of it. So basically, they got energy. Like, this worked and made energy. The problem with this is that the lasers took 400 megajoules to power. So the problem with this method, you might ask, is where did the loss of megajoules happen? Firstly, the lasers themselves, it takes a lot of energy to power a laser, a lot of electricity, and not all of that electricity and energy is transferred to the laser itself. It's got a pretty bad ratio of how much energy you have. These lasers specifically are quite old and therefore quite inefficient. This number could be brought down with more efficient lasers, but it'd still be nowhere close. And also, the transformation from lasers to X-rays, so this, what the Hochulrum does here, when it transforms the lasers into X-rays to compress the pellet, is also very inefficient. It uses up basically 80% of the energy. So you have an 80% energy loss, which right now, with the amount of energy they're getting out, still means that overall, they're losing a lot of energy per reaction, which is something that the news won't tell you because they want to make this look cool. But basically, this isn't really a viable method for energy production. It's a proof of concept, which is great. Like, we know that nuclear fusion can bring out more energy than we put in, but this reaction lasts 10 billionths of a second, produces very little energy, and is extremely inefficient. So what's important to remember here is that this is for military research and not for practical application of energy making research, sadly. So this is to learn how to make better bombs, basically. So I believe that this won't be how if we get nuclear fusion to make electricity, this won't be the way. You'd have to chain enormous amounts of these reactions extremely fast to get any kind of consistent energy production. And right now they can fire one of these a day, basically, and they need to fire thousands a second to get any good marginal production of electricity going at a stable rate. So I might have gone a bit fast. If you have questions, I'm completely open. I might not be able to answer everything because I'm not a specialist, but I'm open to questions. And if not, I can go back and maybe explain some more stuff if we have time.